From asset creation to behavior engineering and animations, creating a game is full of interesting challenges. We strongly believe that machine learning can help in solving a lot of these challenges. So our mission is to democratize machine learning, to make it as easy to use as possible for you, so that everyone can use it. Even if you're not an expert, you could use these tools. I am Vincent-Pierre, and I'm here to talk to you about machine learning agents. It is a toolkit meant to help create behaviors using machine learning in games. Let's get started with a question. When is machine learning useful? It's not useful all of the time. Let's look at an example about credit card fraud detection. Credit card fraud detection is as old as credit cards, and to protect ourselves from it, we've been creating tools to try to detect it as early as possible. Before we had machine learning, we used rules-based engine. With these engines, when a new transaction is made into the system, it is compared with a set of conditions. And if it meets this set of conditions, then it is flagged as fraud. These conditions, these rules, are created by a human. They are handcrafted, and they can look something like this. If a transaction is repeated far away from the billing address of the credit card holder and in a gas station, then it is a fraud. This takes a lot of time to create because a human has to think about all of the possibilities and all of the edge cases and has to account for it. It also requires a lot of maintenance because these rules must adapt and change when the behaviors of fraudsters change. For example, with what I was saying previously about repeated transaction far from the billing address, maybe fraudsters that learn about this rule will start making transactions close to the billing address of the credit card holder. There are also other problems, such as, for example, if the human creating these rules is biased, or if he forgets about something, then the engine will have the same problems, will have the same defects. Nowadays, we use machine learning models. All you need to train a machine learning model is to have data. And with credit card, there are tons of data, all these transactions that are stored. It is usually also higher performance because the machines can look at patterns in the data that are maybe not intuitive to us humans, but that can explain and can predict fraud a lot better. And credit card fraud detection has gotten a lot better since we started using these machine learning models. A machine learning model is just a mapping from some inputs to outputs. So in this example, the input is a transaction, and the output is it fraud, is it not fraud? This improvement has not been limited to just credit card fraud detection. There are tons of domains that have benefited to machine learning models. For example, in image recognition. With image recognition, your input is an image, and your output is a label. What is in the image? Is it a cat? Is it a dog? There is also, for example, translations. Translations, the input is a sentence in a language, and the output is a sentence in another language. And we have a lot of data to train these models. The same thing could be done for game development. And this brings me to what machine learning agents is. It is about using machine learning to create behaviors in games. When we formulated the behavior problem, like how to create behaviors in game, we formulated this as a machine learning problem. And then we used the Unity engine to create the data to train this model. And we can have all the data we need with Unity because a game is like a virtual world. It's a world in which you control everything, and you can collect data from this world as much as you want, as much as you need. Before we dive into how we use this toolkit, first let's define what is an agent. An agent is something that performs actions in the environment. It can interact with it. So at any point in time, the agent is in a certain state. And from that state, the agent collects observations. So it just looks around and sees what's relevant and stores it. Then, from these observations, it takes a decision. It thinks of an action and then performs this action. And to do this, it uses this policy. The policy is the mapping from observations to actions. And this is what we want to train. We want to train this policy using machine learning to figure out this mapping from observations to actions, that we figure out what's the behavior, what the agent is doing when it's seeing something. How do we use agents in-game? We see a lot of use cases for agents. For example, you could have your agent be a player agent, meaning it would play the game with the point of view of the player. That can be very useful, for example, if you want to test your game. If you want to test your game, you have your agent playing through the levels, and you can also assess difficulty. If the agent never figures out the solution to beat the level, then maybe that means the level is too difficult to solve. We can also have non-player agents. These are the NPCs in the environment, the characters the player can interact with. There can be opponents, NPCs that try to fight against the player. They can be companions that try to help the player, or just completely neutral, passerby characters, for example. The third type is invisible agents. Invisible agents can manage aspects of the game without being visible by the player. They can, for example, create content. They manage parameters into the game also. They could, for example, tune difficulty or monitor player engagement and adapt, react to it, and take actions to engage the player more. With the Unity engine, we can create a lot of different kinds of game. There is not one Unity-type game. We can create all of these different things, and we see use cases for agents in all of these scenarios. In any game you can imagine, there would be a use for an agent. For example, in a fighting game, you could imagine an agent that learns to fight against the player. If you had an exploration game, you could have an agent create things in the environment, create things as the player explores to keep engaging him. How do we train these agents? How do we use the Unity engine to train these agents using machine learning? There are two main methods. There is reinforcement learning and imitation learning. Let's look a little bit into the details of what reinforcement learning can do. With reinforcement learning, the agents learn through rewards. This means that when the agent performs something that is good, then you reward the agent. And when it does something bad, you penalize it. This means that the agent learns from just interacting with the environment by trial and error. And this means that since it's just the agent interacting with the environment, you can speed up the game a lot because you don't need human interaction. So this means that you can get these simulations running very, very fast. And this can give you superhuman abilities. And that is because since there is no human input, the agent is not constrained by what would a human do. It just finds what's the optimal way to solve the task. Let's look a little bit more into the details. First, when the agent is in state, it collects an observation. It looks around. Then it uses its policy to figure out what's the action it wants to take. So then the agent takes the action. And then, depending on the result of that action, what happened, then the agent can, or maybe didn't, receive a reward. And the agent uses this reward signal to shape its policy in order to change maybe what it would do next. If this observation is something similar comes up, maybe it do something else, depending on the reward it received. So when the training just starts, the agent explores randomly the environment. It doesn't know what is being rewarded, so it just starts acting randomly, trying to figure out how the rules work. And then, as time goes by and the agent receives rewards and starts to figure out what is being rewarded, then it tries to do that more. It exploits these things in the game to get as much reward as possible. Let's look at the example. This example is the chicken crossing the road. In this game, the observations of the agent are just this image. It's the pixels in the frame. So it's exactly like what the player would see. And the actions the agent can perform is moving to the right, to the left, up, or down on this grid. The goal of the game, what we want the agent to do, is to take the presents and go to the end of the level. So we penalize the agent when it gets hit by a car, and we reward it when it gets a gift, when it gets one of the presents. Let's look at the training unfold. Training just started, so the agent is just exploring. He's taking random action. He's moving around, doesn't know what a car is, what a present is, so he just moves around a little bit aimlessly, up, down, takes a present, gets hit by a car, and gets some signal from this. So just an hour of training, you can see that the agent tries to get the presents. He's not very good at it, he still gets hit by a car, but he's still learning. And I think a human would probably at this stage could be doing better than the agent here. So he's getting the presents, but still loses regularly. Now, after 6 hours of training, the agent has achieved superhuman capabilities. He's just taking all the presents as fast as possible, and he just doesn't get hit by cars anymore. This is something I don't know about you, but I would not be able to play the game like that. Just running as fast as possible upwards, getting as much presence as possible, and just doesn't get hit by cars. Let's look at this second type of training methods. There is imitation learning. With imitation learning, instead of shaping the policy of the agent through rewards, what you do is that you provide the agent a set of demonstrations. So you show the agent what you want it to do. Since the agent learns from what you show it, it doesn't take as long as doing reinforcement learning, because the agent doesn't need to figure out how the environment works, what is the reward, like what to do to get to the reward. It just imitates what the player is doing. The inconvenience is that since you have to show to the agent what it must do, you cannot speed up the simulation. You have to actually play the game at real speed, and you have to give some time to do that. The advantage is that this can give you human-like abilities. So for example, if you play the game, but you always do something that is maybe not optimal, you have something that you always do, but is not really useful, then the agent will start picking up on that and will reproduce it. And that can give agents that look like they're played by a human, even though it's the agent controlling it. Let's look at an example. This example is using Anti-Graviator from Walrus Cybernetic. And on the left here, it's the human that's going to play the game. The human just takes the turns and takes the turn when the road is turning. And the agent here is going to try to imitate what the human is doing. So this just started, so the agent doesn't know when to turn, why is the road turning, when to do what, because it just started. It's like a brand new agent. But bit by bit, by looking at what the human is doing, in which cases is the human turning right, in which cases the human is turning left, when is the human accelerating, the agent is going to pick up on that. And as long as the human is playing here, the agent is going to collect these informations and going to use them to shape its policy. So you can see here, after just 30 seconds of training, the agent is already starting to take the turns at the right moment. This is after 5 minutes of training. After 5 minutes of training, the agent is copying what the human is doing. They started at the same point here, and they're at the same pace, more or less. The agent is providing a challenge to the player, is doing the same thing. Let's compare the two methods side by side. When we use reinforcement learning, we can get superhuman abilities. And this can be useful if you want to test a game, if you want to have the human having superhuman abilities to try to figure out if it's actually solvable. This is one of the use cases, doing QA testing. But you can train your agents with reinforcement learning to do anything. Imitation learning, you might want to use it when you want to have an opponent that looks like a human. So that, for example, if I was a player and I was playing against an agent that was superhuman, that would just be unbeatable, I would get pretty bored very fast. But if the agent is trained with imitation learning, maybe it would have skills comparable to mine and would provide me a more fair challenge. Let's get to how do we train agents using the machine learning agents toolkit. How do we do that? There are 3 steps. first, you set up your game, you set up the environment for the agents, and you add up a few components we're going to talk about. Then you train your agents. The training process happens in Python. We use Python to do machine learning because it is where state-of-the-art frameworks are implemented. So for example, we use TensorFlow to train neural networks. The neural network is the model. This is what we want to train. And then, when the training is finished, you can take this model, you can take the neural network and put it back into the game. So that when it's put back into the game, you don't actually need to connect to Python anymore, and you can just ship your game as is. Let's look at how do we set up the game for training. This is a simplified version of what it would look like. On the left here is what's inside of Unity. We have two agents here. The agents, remember, we defined them. They collect observations from the environment, and they take actions. To take these actions, they need to have the policy. The policy here is held by the brain. So when the agent collects an observation and wants to know what to do with that observation, what is the policy, he will ask the brain for what is the next action, and then the agent will perform this action. Here we have two agents that share the same brain. This means they will share the same policy. This means they'll have the same behavior. You can have multiple brains in the same scene, controlling different types of policies for different types of agents. And then we have the academy. The academy is here to synchronize the brains and is responsible to do the training and communicate with Python. Because remember, this is in Python that the training happens. Now let's talk about the training of agents. Like I said, Unity connects to Python and performs the training over there. And we have implementations of reinforcement learning and imitation learning. And we added a few features. And let's look at some examples of these features that we have in the toolkit. We have these environments that we provide as benchmark just to show what is possible to do with machine learning agents. And for example, the third one here, so on the top, the third one is a tennis environment. In this environment, two agents are playing against each other and trying to score points. They're just playing tennis. And this is to showcase agents playing against each other. The one in the middle is the banana collector, and it's to show how to do imitation learning. So you can play as the agent and try to collect the yellow banana and avoid the blue bananas, for example. And then the agents will imitate this behavior. We have also, this is at the bottom, at the middle of the bottom, we have locomotion environments. So this is when the agent is fully controlled by your neural networks. This means that all the limbs are controlled by the network. So there is no animations in those. Let's look at a few of these examples into details. This is the 3D ball environment, and this is one of the first one we made. Here, the goal is for the platform to maintain the ball on top for as long as possible. The observation is the orientation of the platform, the displacement of the ball relative to the platform, and the velocity of the ball. And from these observations, the agent tries to balance the ball, and the set of actions that it can perform is to rotate either in the x-axis or rotate into the z-axis. Let's look at what the agents do after training. After training, they're able to maintain the ball, and they just don't drop it at all. You'll notice that here we have 12 agents. These 12 agents use the same brain. They have the same policy. And you can imagine scenarios where it would be useful to have a lot of agents with the same policy. This is, for example, a game where you would have, let's say, an army of minions that would try to fight against the player. They behave the same, and they all try to attack the player. And the player must defend itself against them. Let's look at another feature. We have curriculum learning. With curriculum learning, you can make training easier and faster for your agents by setting up environments that are easier to solve and then increasingly make it harder. By making the game harder, the agent will learn to solve difficult tasks by first solving easy tasks. This is similar to the way humans learn. For example, you learn to do additions before you learn to do multiplications. This is the same here. In this example, the one on the right, the agent, the blue block, is trying to get to the green goal. And you can see that at first there is no wall, so the agent can just walk straight to the goal. But as the difficulty increases, the height of the wall will increase, so much that at some point the agent will have to use the block to jump off top of the block, then over the wall to get to the goal. Let's look at what it looks like when it's completely trained. The agent learns to push the block against the wall and use it to jump over the wall to get to the goal. And when the wall is small enough, the agent can just hop over it. We'll see that soon. So he's able to push it here. And when the wall is small enough, he can just jump over it. This environment reminds me of the first time we created this environment, we kind of coded the agent wrong, and we gave him the possibility to float a little bit in the air for just half a second or something. And the agent learned that instead of jumping over the wall, it could just jump around the wall. So it was really weird. It would like jump over the void and then like try to come back on the other side of the wall. And when we saw that for the first time, are we this bad at coding games? and so we fixed that to force the agent to have to jump over the wall. But this was like the first time we did QA testing. We had a game that was buggy, that you could exploit bugs into the game, and we figured it out thanks to reinforcement learning. Another feature that we like very much is to enable agents to have memories. When you enable your agents to have memory, you can do cool things like this. For example, in this environment, the agent, the blue block, must go to the gate with the color that corresponds to the one of the block. This means that the agent must first get to the block, look at the color of the block, then pick the gate. But the agent can only see in front of itself, so it would be easy for it to forget, oh, I saw an orange block, I must go to the orange gate. This is what memory does. It enables us to do this. And let's look at the environment when the agent is fully trained. It can first look at the block, and then it will get to the gate 100% of the time. And this can create some very cool things. For example, if I removed the block from the scene, the agent would be looking for a block. It would not even try to get to a gate because it didn't see the block in the first place. So it would just try to find the block, never being able to solve the game. That is because I took away the means to solve the game. Enabling memories into agent can be very useful, for example, if you would like an agent to be able to find something into a maze. If you don't enable memory, the agent might just explore the maze forever, not remembering where it's been and what it's seen. But if you enable memory, the agent will be able to remember what it has explored and will be able to get to the goal eventually. Another feature, tons of features here. This is multi-agent. So you can have, remember when I said you can have multiple brains in the same scene? Here we trained a soccer environment in which two agents, one that attacks and one that defends, are playing with each other against another team. So here we have an agent, the goalie, that tries to protect the goals. And then you have the attacker that's trying to score goals against the other team. Let's look at what this looks like. You can see here that the two blue agents are working together to try to put the ball inside of the red goal, and vice versa. This can be very useful in a lot of games. For example, if you would want to have, I don't know, two different types of agents, let's say a dragon and a wizard fighting each other. You could enable that by having different brains to have different policies into the same environment. You'll notice something that might look odd is that the agents are kind of always looking at the same direction and walking on the side of the field. That is because we did not enable memories, and the agents can only see in front of themselves. This means that in order to keep track of what's going on in the field, they learn that the best way to do that is to stick against the wall of the environment to keep as much things in front of them. This is the kind of behaviors that emerge, because that is the optimal way to solve the game. And if you were playing this game with a first-person view, you would probably be doing the same thing. The latest feature we added to machine learning agents is curiosity-driven exploration. So this is very recent, it's in version 0.4. In a lot of the environments we have very dense rewards. So this means that the agent gets a lot of signal to shape its policy. But in a lot of games, and in this environment in particular, the agent only gets rewarded at the end. That's probably how a game looks like. You only tell the agent that it succeeded in solving the game when it actually solved the game. You don't give rewards on the way. So if the agent has to perform a very long sequences of actions, have to fulfill certain steps before being able to solve the game, it might not get enough signal to be able to train properly. So we enabled curiosity. And curiosity is the agent is giving itself rewards when it's unable to predict what's going to happen next. Let me explain. The agent tries to predict the consequences of its action. And when it mispredicts, then it gets rewarded, because we want the agent to try that again. We wanted the agent to come back at it and keep exploring until it fully understands the environment, to explore as far as possible. This is very similar to the way humans learn, or like babies, for example. When you give a new toy to a baby, the baby doesn't understand the new toy and will try to play with it until it understands everything it can do. And as long as it's surprised, it's going to keep learning from it. To show how curiosity works, we have this environment called the pyramid environment. Here, the agent only gets rewarded when it gets to the golden brick. You can see a golden brick in the second image. And in order to get to that brick, the agent must fulfill these steps. First, it must activate a switch that is somewhere in the environment. Then it must find the tower, because the golden brick is on top of the tower. Then topple the tower, and then eventually get to the brick. Only then is the agent being rewarded. This is usually very hard to learn because this is such a sparse reward signal. Let's look at what the agent does when we don't have curiosity. When you don't have curiosity, the agent didn't get to the golden brick enough. So it didn't get enough reward signal to shape its policy the right way. So it's kind of just exploring randomly, moving around, doesn't know what is being rewarded, what is worth doing, so it's just moving around without goal. And that is extremely sad. So we will enable curiosity now. And with curiosity enabled, the agent explores the environment as fast as possible, finds the switch, activates the switch, then it must look around for the pyramid, finds the pyramid, breaks it apart, and then, only then, can get the goal, and then it gets the reward. So it learns to do this very long sequence of action, and will perform this sequence of action all of the time. It will explore. If it needs to press the switch, it will explore as long as the switch is not pressed. This feature is extremely useful in games where you have, again, a very long sequence of actions you must perform before solving the level. Now let's talk about taking these machine learning models and putting them back into games. This is a very hard problem. There is not a solution that works well on all of the different platforms that Unity supports. This is hard because you want to be able to balance for the performance of the model. You want the model to run fast. You also want the model to preserve battery. You don't want to spend too much battery on running neural networks. You also want to make sure that the library you use to do your neural network is very small, so that it can fit on the device. This is the solution we have right now. This is as far as we've been. We have TensorFlow with C# bindings that allow you to run neural network models on Windows, Mac, Linux, and on iOS and Android. And just with that, we can already do some pretty cool things. And I have a demonstration here where I have a game onto an Android phone. This is the good boy demonstration. In this environment, the little dog here is controlled entirely by a neural network. This means that the motions of the legs are directly controlled by the policy. There is no animations. We did not code an animation for the dog to walk around. And I can grab the stick and throw it to interact with this agent. And sometimes it does little cute things. It can do little flip, will roll around. I've seen it sometimes do a backflip. And we did not encode that. All of this emerged. We did not code for it. It's going on the side, it's rolling on the ground, doesn't know what's going on, throwing the stick. I could play for hours this game. I've lost so much productivity just since I got this in my hands. Come on, get it, go get it. This is running neural networks inside of an Android phone. Come on, puppy, come on, get me the stick. Stop being cute like that. Good boy, good job. Good job. Well, we have more things to talk about, so I'll go back to the presentation. If you want to play with this, you can come see me afterwards, and you will see that it runs just on the phone. Now, what we want to do next is to be able to provide neural network inference. We want to put machine learning in as many devices as possible. So we want to support all of these platforms. And we want to leverage the incredible work that's being done on a lot of these platforms. Because a lot of people are trying to solve this hard problem. And at Unity, we want to be able to take all of these solutions and provide them to you, the developers, so that you don't have to think about which library to use on which platform in order to get your machine learning models to work. This is what is currently included in machine learning agents. So we've talked about some of these features like memory-enhanced agents and curiosity. I want to talk a little bit about Docker. So we managed to put everything that is Python, TensorFlow related inside of a container. So Docker allows you to put processes, so you don't have to install Python, you don't have to install TensorFlow anymore. You can just download this one application, Docker, and you can train your neural networks directly. We have also in-editor training now, meaning that you can train your agents inside of the editor window. You can do it like that. You can just press play in your editor to start training your agents. And this allows you to iterate a lot faster because you don't have to build your environment in order to train it anymore. Because it is our mission to democratize machine learning, the project is completely open source and free to use. It is on GitHub at this address, so you can go there and start using it now. We are at version 0.4 right now. We just released Monday. If you have a question, you can contact us directly. And I have other things to say. It's that we have now a nano degree with Udacity. You can get a discount for it, and it's a nano degree in deep reinforcement learning. We worked with Udacity to create this degree, and it uses machine learning agents. So now you can learn to use deep reinforcement learning with the toolkit. We have also a hands-on lab session at 1:30 today in breakout room 2, where you can get your hands directly on machine learning agents and start using it today. Is that all? And that is all. Thank you. Are there any questions?
Hi.
Yes? The training of NPCs, how it would look like. So if you want to train the editor, for example, you would set up your environment, you would set up your agents, meaning you would tell them what they need to observe and how they would act, depending on what the neural network tells them to do. And then you would start the training session. You would see the agents first trying things out, just exploring randomly. And eventually, as the training unfolds, the agent will learn what to do. Their policy will start to take shape, and they will start to do the things that get them rewarded. So in the balance ball example that I was showing, at first the platform would just probably not know what to do and would just drop the ball all the time. And then as it drops the ball, it would get a negative reward, a penalty, and it would try not to do that anymore. So then it will start keeping the ball a little bit longer, and then a little bit longer, until eventually it just doesn't drop it at all. Yes?
Hi. I wanted to know about the memory. How do you choose what the agent will remember and for how long will it remember?
So that is an excellent question. How do we do memory? How do we make sure that the agent remembers the right things, the appropriate things? That is, the agent learns, actually, what is important. So the agent might see, for example, in the example with the block, and the agent needs to find the gate with the right color of the block, the agent would first see the block, but maybe it would not know at first that it's relevant. So maybe it would just ignore it, would maybe discard this information at first, and then start getting to a gate, and oh, maybe it would get the point somehow. And then the agent would start realizing at some point that it must remember the color of the block. So we'll start looking for that information. So it's kind of, we don't specify at all, pay attention to this, pay attention to that, remember this. The agent learns to do that on its own. It learns to pay attention to what is relevant to get the rewards.
Okay. And also for the duration, for example, you may need to know the color right now, but in the future you might not need it.
So we use long short-term memory, LSTM, and this basically means that the memory you have from the previous step goes through a small neural network, and you get a new memory for the next step. So this means that some information can be passed across steps, and it's the agent's responsibility to figure out how long it must keep the information. So the agent figures out, oh, this information I only need for 5 steps, this information I need for 20 steps. Usually with LSTM, the way we have implemented it now, it's something usually around 30 steps of the network that the agent is able to remember well.
Okay, thank you very much.
Hi. So if I understand correctly, the training can only be done in Unity or before shipping. So do you plan on implementing a small training runtime so the games can adapt to the players at runtime? For example, for difficulty adjustments?
When you mean runtime, you mean, for example, on the phone?
Yeah, on the phone, on the laptop.
So so this is something a lot of people want to see, is agents that can train while the player is playing. The problem with this is that, remember when I talked about reinforcement learning, it's that it takes usually a lot of time for the agent to learn properly. So we speed up that simulation. If you require human interaction, then you cannot speed that up eventually. So it might take a very, very long time in order for the agent to figure out what to do when the player does such and such.
Yeah, but for example, for the imitation learning, it would totally be possible, for example, for the racing game, that the opponents learn from the actual player and the difficulty of the game adjusts to the player.
So so doing imitation learning on devices is also extremely expensive for the training of the network. Training a network on a phone is not something we plan to do. It's something extremely hard to do, and it comes at the cost of the battery and the time it takes to run, like take a bunch of observations, usually a humongous batch, and just do one pass into the network to train it, can take a lot of time, and that could decrease the quality of the game. There are other ways, though, to make sure that you can have an agent that adapts depending on the player, and that would be to have a fully trained network that would take as observation what is the human playing. And so when you train it into a variety of scenarios, like this is against, and for example, you could train an agent to imitate the player, and you could say, this is against a very stupid agent, doesn't really know what to do, and this is against an agent that is super strong. And then the agent would learn, like, what to do against which agent. You could reward it, for example, not by you were able to beat the player, but you could reward it by you were able to beat the player just by that much. And so the agent would learn to kind of adapt to the level of the opponent to maintain engagement. That is more what we see for agents that can adapt to player gameplay.
Thanks.
Hi, thanks for the talk. The chicken road example used for observation the entire screen image, right?
Yes.
As an alternative, if you'd given it the positions of the things in the scene, would that have yielded a faster result for success, or why did you choose the whole screen?
We have not tested that, but I believe yes, because you give smaller information, you kind of chew up the work for the agent. Instead of having the agent learn, oh, this looks like a present, this is a present and it's over there, you could just directly feed that information to it. So it would learn faster.
Okay, thanks.
The reason we use Pixel is to show that we can learn from a variety of things. We can learn directly from images. And that could be useful if you want, for example, an agent that imitate what the human would do. You would want to give it the same input the human has. You wouldn't want to give it an unfair advantage, giving information that the player playing the game would not have access to. This would be useful for if you want to test your game.
Thanks.
Hi. Sorry. About the imitation learning, the agent is learning by imitating the trainer. Is there any chance that the agent is better than the trainer?
So with imitation learning, the agent learns to just imitate the human. It will never be able to be better than him, because if you never show it what is good, you would not be able to learn it. It would be able to mimic at best.
It's like the human make mistakes, but the agent learn by taking the best actions of the human, but not making the mistakes. Is this possible?
You would need to define what is a mistake, for example. So that would require you to have, in addition to play the game, have someone telling, "Ooh, this is good. Ooh, this is bad." We could imagine something like this. We have a feature when you train your agent. We have a record button. So you have a button to start and stop the recording, so what the agent must pay attention to. And we have also a button to clear entirely the buffer of previous observations. So this means that when you press this clear button, all the past information, the past gameplay you provided will not be used for training anymore. And so you could do that. Like if you do a mistake, you could say, I did a mistake, like erase the memory and let's start a new recording to make sure that the agent doesn't learn from that mistake I made there.
Okay, thank you.
Hey, a question following on from a question earlier about providing the data as opposed to the image. Right now, is it set that you have to hard code the score for the reinforcement learning to learn from the score? And is there any future implementation considered for using maybe a score CNN image for the algorithm to learn?
So you mean having the reward signal come from the image?
Yeah, so learn from like a score in the top right, like use a CNN to pull that.
So the thing that you would still kind of need to, because all games are different, you would need to have a consistent position of the score, so you would need at least to provide information on what is it you're trying to maximize.
Yes.
So we wanted to provide an easy and fast way to provide rewards directly. So this is why you kind of have to code. You give rewards manually to the agent inside of the code.
Yep. Also, I noticed that you said you were using TensorFlow and Python. Is there any plans for other frameworks in future?
So we use TensorFlow because we can put it on phones right now. But there is a low-level API. So what we provide right now for training is a very high-level API where all you say is, I want reinforcement learning with this environment. But we also provide a very low-level API that will allow you to connect directly with the environment. So you can do your own algorithm. You could use your own frameworks. You could use PyTorch or other libraries to do neural network training and directly collect observations from the Unity scene and send back actions to the environment for the agents to perform. So you could train your own thing. You can do your own research with that.
Awesome, thank you.
Hello. My question is, I tried also machine learning, and I found out that sometimes it just doesn't work. And because it's encapsulated in TensorFlow, it's impossible to debug, at least in current state. You have some tips or tricks or some future plans to finding out why it's not doing any actions at all or why it's not learning?
So there are, right now, there are kind of roadblocks. Right now, there are some things that, for example, if the agent doesn't learn at all, most of the time it's because it doesn't have enough information to solve the problem. So that usually means that since you're kind of responsible to tell the agent what it must pay attention to, you must be careful when you tell what to pay attention to, because if you forget something, the agent will not be able to learn. For example, in the balanced ball environment, if I forgot to give the position of the ball, the platform would not know what to do, would not be able to solve the problem at all. About not performing actions, we provide with the brains player brain, so that allows you to take control of the agent, so that you can test if you can actually input actions for the agent.
So just experimenting and trying different observation, different sets of observation.
Yes, I would say more observations is usually better. It's better to give too much than not give enough.
Okay. And quick another question. Are you planning to also introduce, to speed up learning, multi-threaded learning, or on simultaneous machines, or a few machines simultaneously?
That is on our roadmap.
Thank you.
Hi, the question is about limitation and reinforcement learning. As I understand, there is 2 modes which can be separately used, but are we able to somehow combine it? For example, to speed up, we start with imitation learning and then switch to reinforcement.
So right now we do not have a framework for that. There is something about imitation learning and reinforcement learning combined. It would probably not look like the way you think. It would probably not be like show the agent and then do reinforcement learning on top of what the agent can do, because usually the agent would very, very fast forget the imitation learning training and just look at the rewards. This is very hard to fine-tune and make it work everywhere. But there are other ways, and that it involves, for example, inverse learning, where from imitation learning, instead of learning what the player is doing, you're learning how the rewards work. That could be a way to do this. And then once you learn how the reward works, you can have very dense rewards that can make reinforcement learning faster.
Thank you.
Hello. This technology probably works better for other games than other. For example, could you use this to create a chess AI?
What do you mean, a chase?
A chess AI.
So this is most useful for reactive AI. If you wanted to do chess, you would probably need a lot of planning ahead, exploring different possibilities. And that would probably take too long for these algorithms to learn. But we could combine these eventually with other techniques that involve planning, for example.
All right.
That's all? All right, thank you very much. Don't forget, there is the hands-on lab later.
I have one more question if you have the time.
Oh, sorry.
Could you talk a little bit about how the dog learns how to move?
So this is directly controlling locomotion. So the observations of the dog here are where is the dog relative to the target, and what is the orientation of the dog in space. So it's like where are the legs, what's the bending of the articulations, and the control is directly applying torques to the joints of the dog. So this means that the network learns from what's the position of the dog, how to put force into the muscles to be able to walk, grab the stick, and bring it to me. All right, so again, project's open source. You can go try it out right now and go learn reinforcement learning right now with Audacity. And hands-on lab later today at 1:30 in Breakout 2. Thank you.